Hi, my name is Josh Greenwell, and I'll be presenting Low Input and High Diversity, Restoring Minnesota Grasslands with Energy Landscapes. Here's a quick outline of the presentation, overview of everything that's happening. So why should we care about energy? Well, CO2 emissions are increasing every day, and according to co2now.org, we emit 36.7 metric tons per year. The increasing CO2 will cause negative effects to the Earth's atmosphere and climate by increasing greenhouse gases, which will increase the Earth's temperature. The increase in temperature will affect crops and animal habitats, potentially causing a decrease in food production or some species to go extinct. Fossil fuels are 91% of CO2 emissions. Therefore, if we reduce fossil fuel use, we reduce carbon emissions. To reduce fossil fuel use in Minnesota, we can use low-input, high-diversity biofuels. Now, one of our other issues is ethanol. Ethanol from corn is ineffective. The amount of corn used to produce the ethanol in a gallon of regular gas would feed a person for an entire day. The production of ethanol requires so much fossil fuel energy that it only has about a 20% energy benefit. The cost of gas made with ethanol is actually higher per mile because ethanol reduces gasoline's energy per gallon. An article I read called Powering the Planet said that there's no easy way to switch to clean energy. It'll depend on the land you have. You can get wind energy if you have the right area, and that'll be cheap. And you can use solar, but that's not always good everywhere. Basically, we'll have to use a combination of different renewable energies depending on the climate and weather to find the most efficient way to power the planet. In this article, we can solve climate change, but it won't be cheap and easy. It explains that most people are coming out with scenarios on how to solve problems, but those are just thought experiments. They're not concrete roadmaps on how we can actually solve the problems, and we need to focus more on those roadmaps. If we don't fix the climate change, we'll run into problems such as market failure, political distortion, and unforeseen events. Also, we have the greatest energy intensity in the last 40 years. Here's a graphic that shows potential land use intensity in 2030. On the left side, you can see all the different energy types, as well as what their potential land use will be, kilometers squared per terawatt hour per year. Another article I read is called Carbon Negative Biofuels from Low Input High Diversity Grassland Biomass. The high diversity grasslands had increasingly higher bioenergy yields that were 238% greater than monoculture yields after a decade. A monoculture yield is something like corn, where a high diversity grassland is a grassland with multiple plants and perennials. The annual carbon storage in soil was a logarithmic function on the graphs, basically stating that as carbon was sequestered in the plant, some of it would go down into the soil, and every time the plant was cut and regrew, it would store more and more CO2 in the soils. Now, low input, high diversity biofuels are carbon negative, leading to net sequestration of atmospheric CO2 across the full life cycle of biofuel production and combustion. And what carbon negative means is basically that the low input, high diversity will sequester CO2 in its plant, then be cut and used for energy, and then regrow, taking in that same amount of CO2 that it released when being cut, as well as taking in a little bit more into its roots every time. Since you're not digging up the roots of the plant, you'll gain more CO2 storage. This graph is from the previous article, and it shows the ratio of energy output to energy input per biofuel. So if you look at corn ethanol, this first bar, it shows that the energy output is about 90 gigajoules per hectare, but you only end up with about 18.9 gigajoules per hectare as your energy because of how much input energy is needed to create the ethanol. If you look down to the right side, you notice that you have a low energy input with a much higher energy output in comparison for low input, high diversity prairie bioenergy. Now, if we enhance prairies by converting corn into low input, high diversity grasslands, how many square kilometers of habitat would we gain? How much energy could be provided by this landscape? So what I did is I made a map of the preserved grasslands in Minnesota and put a 5 kilometer buffer around each one. That's the map on the left. And then on the right, we have the corn crops in Minnesota. So what I did is I took all the corn and found which parts were inside of the buffered zone of the preserved grassland. Here's the map I got. Now I zoomed in one of the clusters at the bottom to show what one of the habitats looks like and all the corn surrounding it. So now we're going to want to calculate the actual land use of those areas. Switching the corn to low input high diversity in the buffer zones is going to be calculated by taking the grid cell size, which is 190,969 square meters, and multiplying it by all the corn cells that were found in the buffer zones, which is 3,900. And that number that we get will be converted into kilometers squared, which comes out to 746.9. Now we want to calculate energy. Minnesota produces 4,786 gigawatt hours of electricity per year. If 1 hectare of low input, high diversity produces 28.4 gigajoules of energy per year, then we can convert 1 hectare into 0.01 square kilometers and take the 28.4 gigajoules, times it by the 0.01 kilometers, and then by the number of kilometers of land we have, giving us 212.1 gigajoules per year. Now, since Minnesota is producing gigawatt hours and we have gigajoules, we're going to want to convert that into gigawatt hours. So we take the 212.1 and we convert it into megawatt hours, which is 58.9, then to gigawatt hours and multiply it by the number of hours in the year, giving us 515.96 gigawatt hours per year. So in conclusion, changing the corn to low input high diversity in a 5 kilometer radius of protected lands will yield 515.96 gigawatt hours per year using 746.9 square kilometers of land. Now the 516 gigawatts is 10.8% roughly of the 4,786 gigawatt hours used by Minnesotans every year. Although this doesn't solve the CO2 problem on its own, it has other benefits. One benefit is a way to move away from ethanol. We know ethanol is bad because it only produces about 20% as efficient, as well as the other problems stated above. It is also good for habitats and helps the ground nesting birds because it gives them a safe place to go, and can be done on degraded lands. So we won't have to worry about rotating crops or anything. We can use a low input high diversity on places where you wouldn't be able to grow corn or soy. This is a good starting point to move towards renewable energy as well as conserving habitats. So for future research, now that we know how much energy we can produce per square kilometer, we can determine how much land would be needed to power Minnesota and how much energy we can produce replacing larger amounts of ethanol crops. This could help us find a more efficient and clean way to produce biofuels. Also, we can study the habitats to see if a 5 kilometer buffer is large enough area following the conversion from corn to low input high diversity. If it's not, we can increase the buffer and see if that helps.